Bismillahir Rahmanir Rahim. So, this lecture is about phasors. So, let us consider a sinusoid. Uh, V of t is equal to Vm cos omega t plus phi. So, this is a sinusoid in time domain. Note that though we are using cos here, it is still called a sinusoid, right? So, let's also consider the following complex number uh, Vm e j omega t plus phi, right? So using Euler's identity, this complex number can be written as Vm e j omega t plus phi. It can be written as Vm cos omega t plus phi plus jVm sine omega t plus phi, right? So this is the real part and this is the imaginary part. So if you compare this expression here with this one here, so this real part is our required sinusoid here, right? So what we can do is we can write v of t is equal to the real part. This already represents the real part of this complex number, right? So Vm e j omega t plus phi. So the real part, which is this one, of this complex number is this sinusoid here, right? So let us manipulate this complex number further. So this can be rewritten as Vm e j omega t multiplied by e j phi, right? So this can be further rearranged Vm e j phi. Just swap these numbers e j omega t. So this is the this term involves time and is variable, but this Vm is a constant here, phi is a constant here. So we can write it like this: R e v e j omega t, right? Where this v bar is equal to this Vm e j phi. Or we can write it like this: Vm angle phi in polar form. This is the exponential form, this is the polar form. So this V bar here is called the phasor representation or phasor domain representation of this sinusoid here, right? This frequency and time, this time domain term is expressed here, right? So this is phasor domain representation uh, of the sinusoid. So in short, what we can say is a phasor is a complex number representation, complex number representation of a sinusoid. And how does it represent the sinusoid? Using its amplitude and phase angle, while this term omega t is expressed. So it represents a sinusoid using its amplitude and phase, right? So if we are given VFT in the time domain, Vm cos omega t plus phi, so then in the frequency domain, it is transformed as V bar is equal to this Vm here, and we take the phi from here, right? And if we are given this phasor here in the frequency domain or the phasor domain, so we take this Vm here and put it here, and then we just write down omega t cos omega t plus phi here like this. So this is the time domain representation, and this is the phasor domain. So this is also called frequency domain. Frequency frequency domain, as this omega is a constant, right? And omega is is implicitly present here only. It's not explicitly shown here, but implicitly it is present here. So this is also called the frequency domain representation, right? So to further understand the relationship of this phasor here and uh, this time domain sinusoid here, let us uh, see this rotating phase. Consider this a rotating phasor here, right? So see this phasor here, for example, and it this is angle phi here, and this is pose Vm here, right? And we assume that it rotates counterclockwise with an angular speed omega, right? So and then we see its projection on horizontal plane. This is omega t here, and this is v of t here, right? So suppose initially it is here, this projection is at this point is here at t is equal to 0. Then at some time t is equal to t naught, it reaches here, then its projection is somewhere at this point is here, right? And again it further uh, comes here, right? At this point, for example, its projection is again somewhere here. At this point, it reaches here at t is equal to 0. So it's tracing like this, right? And then further, it reaches here somewhere. So its projection, you see, it's projecting here, its projection. All are its projections at this point. At this point, its projection is right here, right? So at this point, when it reaches here, its projection is somewhere here, right? And then when it reaches here, we have a projection here. So like when it's rotating, you see, we get a projection on the horizontal plane like this, which is a sinusoid again. So this is a Vm here, and this is a minus Vm here. So this rotating phasor at angular speed omega in the counterclockwise direction, it traces a sinusoid on a horizontal plane. So this rotating phasor is also called a sinusoid. Rotating phasor is called a sinor. Rotating phasor is called a sinor, right? So So as we have seen, we can convert this time domain representation of the sinusoid into the phasor or frequency domain phasor right here. What if we have a phasor in the form of a sine, for example, function v1t is equal to vm sine omega t plus phi. So we must first convert it into the uh, cosine form. So vm, it will be vm cos omega t plus phi and minus 90 degrees, right? So the corresponding phasor representation will be Vm angle, this will be Vm angle phi minus 90 degrees. So that is V1, right? V1 is equal to this. So usually we will do this, but occasionally, sometimes we can also represent a sinusoid like this in the form of a sine function directly as a phi function also. For example, if we have V1t is equal to Vm sine omega t plus phi, so we can directly represent it uh, using Vm angle phi also. In that case, when we are performing the reverse operation, then again we'll be using a sine here, not a cosine here then. So transforming back from the phasor domain into the time domain, we'll be using a sine function here if we have used this transformation initially from the time domain to the phasor domain, right? Uh, another important and related topic is the phasor diagrams. So we can represent a phasor using a phasor diagram also. For example, if we have uh, this function Vm uh, cos omega t plus phi, and it is V is equal to V of t is equal to Vm cos omega t plus phi. So using a phasor diagram, it can be represented like this. This is the real axis, this is the imaginary axis, right? And we have this Vm here, right? Or we can simply say V bar in terms of phasor domain, right? This is in terms of phasor domain, it is written as Vm angle phi, right? So we can write V, and this is this amplitude is Vm, right? So we can write Vm angle phi. And if we have another, for example, current, I of t is equal to Im cos omega t plus theta, and in the phasor domain this will be written as Im angle theta. So we can plot I also here, for example, like this. So this is Im and this angle is theta. So a related concept is the leading or leading or lagging of either of these functions. As we have seen in the time domain, we can say that once a particular sinusoid is leading and the particular another one is lagging. So similarly, in the phasor domain, we can say that Vm or V here is leading this other phasor I here. So the angle by which it is leading is this angle, right? And this is phi minus this angle theta here. So this angle is phi minus theta. So we can say that uh, uh, V leads I bar by phi minus theta, or we can say that I lags V bar by phi minus theta.